To evaluate the integral from negative infinity of sine of x over x, mind my unfunny jokes of contour integration, first what you need to do is convert this sine of x over x to a complex plane, obviously. How we're going to do that is, first of all, we're going to substitute in z as our variable to replace x. You don't really need to do it, it's just, I guess, formality or whatever. It's just how I learned it. Now, what we do is, with Euler's formula, e to the I z equals, it's really hard to, like, if I can record this and write, because I don't know if I'm recording the right thing. It doesn't really matter, I guess. Plus I sine. We take the imaginary part of this equation, that's sine, right? We're gonna be left with the contour integral over the path c e to the I z over z dz. What this does is, in the complex plane, when you have a function with e to the I z, e to the I z times f of z, you can use a semicircular contour like this. Yeah, like this. Negative r to r, negative alpha to alpha. What this black thing in the middle is, the black thing, that's the residue of, this function, right? How do we find the residue? What is the residue? Well, it's an undefined point. I misspelled undefined. All this complex analysis can't spell undefined. Undefined point of the function. What's an undefined point in the function? It's where, when you represent it graphically, it blows up to infinity, because you really can't do that. It's like plugging in 0 to to 1 over z. It's just not in the domain, you can't do that. So in this case, e to the iz over z, we can just substitute 0 like so, because there's really no other residue, and you won't really encounter multiple residues in a singular contour at this level. So I thought someone walked past my room. Bearing this in mind, we have our semicircular contour, which is what we're going to use to evaluate it. We're going to call this path C. I mean, that's why that's why I did over here. Call this C. Now, to evaluate this contour integral, we're gonna need to dissect each part of its graphical representation, each part of the semicircular contour, so that we can later on rearrange the equation to find out its value. So what I'm going to do, call this the integral over this semicircle, big gamma, the integral over the residue. Look at my nails. I actually recorded this, but I messed up, lost 15 minutes of footage because I wanted to go to the bathroom. I actually stink right now. I was sweating. You need to know that. Okay, now we're going to integrate along the real axis, negative r to negative alpha, of plus alpha to r. And I forgot to mention, what I did in this is that I took the limit as r approaches infinity, this approaches infinity, and as alpha approaches 0. Typically you would think that this residue would evaluate to 0, because the alphas, we're reaching 0 as well, but that's not how it goes. It doesn't reach 0. You only do that for branch points, which we're gonna learn later on. Okay, now putting everything I said down, we're gonna have a sum of the integrals contour gamma along the path. I'm just zapping. Okay. Now this is important, because we took the limit as r approaches infinity and as alpha approaches infinity. We can actually rewrite this as contour C equals contour integral over the path big gamma plus prepubescent gamma plus the integral over from negative r to positive r, because we're just merging the integrals. Did I even record that? I don't know. I don't care. I don't care. I probably have a list. I'm like, I always stutter and stuff. You don't need to know that. You don't need to know that. So now, I'm just gonna evaluate this integral first to find out what this is equal to, right? Oh, wait, before that, okay. Now, z, I'm gonna have to convert that to a polar plane, right? And to find, now we're gonna have to differentiate dz, because we're going to have to differentiate z to get dz, because we have dz in each of these integrals. You want to find out what its value in a polar representation, and that's going to be in terms of theta. So if we differentiate in terms of theta, we've got IR, EI, theta, d theta. Now, negative r to positive r of our function e to the iz over z, we substitute in polar representation. Where is that? Yeah. We get e to the I REI theta over REI theta I REI theta d theta. These cancel out. We're left with yeah, and I shouldn't have done that. My humble apologies, kind still, sir. What we're just gonna do is substitute in r approaching infinity, and that leaves us with the integral of e to the iz over z dz. My bad. And that's the original integral we're trying to evaluate. So what this means is, if we substitute this in over here, we're gonna have to rearrange the equation. We're gonna have to find out what these are equal to. Rearrange the equation, we get this. Okay, now we know what this is, and we're gonna find out what this is. Okay, we're gonna do the same thing I mistakenly did for the other one for this. My apologies. I'm being sarcastic, by the way. I don't actually say that. My apologies. I REI theta over REI theta times I REI theta d theta. These cancel out. We have contour integral over path gamma I times e to the I REI theta. Okay, so in this semicircle, we have the real, this is supposed to be an R. We have the real axis approaching infinity. We have a negative R approaching negative infinity. We have R approaching infinity. What this means is that this semicircular contour will approach 0. Therefore, contour integral of big gamma will approach 0, as per Jordan Lemers. Some guy called Jordan. I don't even know what Lemers means. In a mathematical notation, we represent Jordan Lemers, what I just said, what I explained as the absolute value contour integral over a path f of z dz will be less than or equal to contour integral of the same function but absolute value dz. So yeah, we're just gonna substitute that in, right? I can't be asked to write this entire thing again, so I'm just gonna do less than or equal to contour integral over the path big gamma absolute value of EI theta times I, because I forgot to write that down. It was d theta this entire time. Okay, now what we're gonna do to simplify this integral, I'm gonna do Euler's formula again. The I theta is cosine theta plus I sine theta. To simplify this, right? Contour integral over big gamma absolute value of e to the I R cosine theta plus I sine theta, theta times I, because I forgot to write that down. Okay, now, I forgot to do this, but in this semicircle, we're going back to this again. Typically, what we do is we integrate counterclockwise, right? Integrate counterclockwise, but around the residue, we integrate clockwise because that evicts the residue. That that's how we evaluate them. And because of this, that means this semicircular contour, wait, that's going in this direction, goes from 0 radians to pi radians. If it was a full circle, boom, it would go from 0 to 2 pi radians, obviously. It looks like Pac-Man. So I'm just going to write down the limits, because I should have done that sooner. Absolute value of I. Okay, now simultaneously what I'm going to do is, when you have any term where its exponent is adding, when you have a sum of exponents in your variable, you can split that up to a product of the same variable or term. I shouldn't call it a variable. I get done for. What that means is we get EIR cosine theta times eta, look, eta I sine theta times I will give you a negative r sine theta, because you know I is root -1. Two of these gives you -1, you know, it's not that hard. D theta. Okay, in this scenario we have less than or equal to multiple complex numbers. E is not complex, you get what I'm talking about though. In a absolute value, and in this case what we can do is split it up. We can take the absolute value of each of these terms separately, and the absolute value of I will be equal to 1. Absolute value of eta IR cosine theta will also be, I need water, oh my god, I'm not gonna, okay, will also be equal to 1. We can prove this with Euler's formula, because when you have eta IR theta, where I is a real number, and you take its absolute value, it just becomes 1. I don't really want to prove it because I can't be asked, right? So that means we're left with integral from 0 to pi. Okay, I thought I was filming my crotch. I shouldn't have said that. That's the value of negative r sine theta. I'm probably going to delete this. D theta is less than or equal to. Now what I'm going to do is, to prove that this becomes 0, I'm going to take the limit as r approaches infinity. And when I do this, we're going to have e to the negative infinity. 1 over e to the infinity, 1 over infinity, we're going to have 0. So that means our contour integral over gamma will be less than or equal to 0. And its absolute value would be less than or equal to 0. The only case where where something can be less than or equal to 0 and you take its absolute value is when it's 0 itself, because if you have the absolute value of -1, have that less than or equal to 0, that's going to be 1. 1 is not equal to 0, so so yeah, so this would be this, that's 0. We cancel that out. That means we only have the integral over gamma. We have this integral which we're integrating clockwise. Okay. Okay, so I'm just gonna convert it to a polar representation, which I did like over here. Yeah, I cancelled that out. Can't be asked to write it again. My handwriting is so bad, so bad. Wonder how a teacher can read it. Okay, so I R A I theta d theta. So I'm gonna convert it to, like, I guess a regular integral. I'm gonna put in It's not really a regular integral. I'm gonna give it limits by doing the same process. I know this is integrated, is being integrated clockwise. Therefore, it goes from pi radians to 0 radians. So I'm gonna write that down. The integral from pi to 0 of I r e I theta d theta. So now what I'm gonna do is have this I moved out as a constant multiple, and I'll just see that later, rei theta. Then now, okay, I want these limits to be switched. I want it to go from 0 to pi, and you can only do that when the integral is negative. So we're gonna have a negative integral, negative I times the integral from 0 to pi y1. Look, I switched the limits of rei theta d theta. Now to evaluate this, evaluate an integral of a residue, we're going to do something called residue theorem, made by a guy called Cauchy, some important bloke. I said bloke in 2025, I'm so cringe. It's not pronounced Cauchy. I used to say Cauchy, but it's actually Cauchy. What this is equal to is 2 pi I times the sum of residues in the function f of z. So if we connect it to our function, which is just rei theta, not rei theta, it's sine x over x. I messed it up. That's our function. We have one, look at this, function at sine x. We have one residue at sine x over x, right? We have one residue over here. It's when x is equal to 0. So that means we can evaluate this with 2 pi I times, there's only one residue, so yeah, we can evaluate it with 2 pi I, right? Why would I find the sum of one term? It's just the term, right? It's just the term. So this will be evaluated to 2 pi I. How can you do that? So that means this entire thing be integrated to 1 in order for this to become I pi, right? And don't mind the negative. So I'm going to do that. Negative I times 1, not 1, z, evaluate, fucking theta, oh my god, evaluated from 0 to pi. What that does is negative I pi. The reason it's not 2 pi I, because we're integrating a semicircular contour. We're not integrating a full circular contour. We're only taking the upper half. We're taking half of it. Therefore, it's pi I. And the reason we have the negative is because I had to switch the limits from pi to 0 to 0 to pi. So with that we have, where is it? It's over here. Contour integral over the path C is equal to negative pi I plus, in the same contour integral. So what we're going to do is contour integral over C is equal to, we're going to rearrange the equation to isolate this, plus equals a positive pi I. So what is this contour integral to begin with? It is the integral of e to the iz over z. I should have written it down first. Dz, we have that equaling to pi I, but that's not what I want. I want the integral from negative infinity to infinity of sine x over x dx. How I find that is, I know Euler's formula. I just take the imaginary part of it, and that's what I'm going to do. Take the imaginary part, contour integral. Someone's at the door. Just gonna ignore them. And dz have to be quick. Equals the imaginary part of this of pi I, which is just pi. This evaluates to pi. Does it? Probably no, it does. It does. Therefore, if we take the real part, we find the integral from negative infinity to positive infinity of cosine z over z dz, which is just 0. This evaluates to 0 because we're using the same method, just a different substitution. No, same formula, just different part of the formula. Okay, bye. I have to go now.